will not move something from one side of the equation to the other, right? We can do that if we're solving an equation, but we're not solving an equation here. What we're doing is we're trying to prove that sine cubed x plus sine x cosine squared x really does equal sine x. So I always, when I do these problems, I draw a line down the equal sign. Nothing can go from one side to the other. So you're either working on the left side of the problem or you're working on the right side of the problem. You do not move from one to the other. So for this example, I need these two things to match. Some of the strategies we've tried so far are changing everything to sine and cosine. It's already sine and cosine, so that's not going to help us here. We could use an identity that we have, but sine cubed x plus sine x cosine squared x, that's not an identity so far. So those are not going to help us. What will help us here is the greatest common factor. What is the greatest common factor for both of those terms? Sine x. So if I factor out a sine x, then if I've got sine cubed x, I pulled one of the sine x's away, so I'm left with sine squared x. And then sine x cosine squared x, I'm taking the sine x away, so I've got cosine squared x. And so that makes us all excited whenever we see it, I hope. Because what is sine squared x plus cosine squared x? 1. I do want you on this, I know it's a pain. Whenever you have sine squared x plus cosine squared x, I want you to write the step where you replace it with 1. Because sometimes, on this one, I'll probably know you knew that was what was happening. Other times, I might not. So we're going to say sine x times 1, and then, of course, that just equals sine x. And then on the other side, I need it to match, which it already did. So I'll just put sine x right here. And so at the end, you should have the same thing on both sides. Okay? So the good thing about these problems versus what you had to do over the weekend is you at least know where you're going. Sometimes that helps you out to know where you're going. It'll let you see what to do. Sometimes maybe it doesn't matter. You're just as clueless either way. On this next slide, I have a list of several strategies. So what we're going to do here is just write down several of the things that might help us when we're doing these problems. Doesn't mean it's going to work on every problem. We might use more than one of these strategies in the same problem. But strategies to try. So one of them is to transform the more complicated side first. Okay, we'll see some of these where we need to do work on both sides of the problem. I usually always try to start with whatever looks the worst. On that last problem, it was pretty obvious. The left side is the one that needed some work done so that it could match the other side. If I really wanted to confuse you, I could go back and do it where I worked on the right side instead, but it is easier to work on the more complicated side first. Okay. Another thing that can help is to substitute basic trig identities to simplify. Okay, so that is things like when you see sine squared x plus cosine squared x equals 1, or sine squared x plus cosine squared x, replace it with 1. Or if you see tangent, you can replace it with sine over cosine. Okay, on that last problem, what did we do? On example 1, we did substitute a basic trig identity, so that's one thing that we did. What did we do before we substituted in that sine squared plus cosine squared? We did greatest common factor. So one thing that you can do is factor. And sometimes it's a greatest common factor. Sometimes it's actually factoring like in sets of parentheses like number 53 was on your homework. And sometimes we actually might not want to factor. Sometimes it's already factored. We might want to multiply it back together. Another thing you can do is sometimes you might want to get like denominators and add. So sometimes your equations have fractions in them, and you might want to get like denominators and add those together. And then the last one I have here is to change everything to sine and cosine. Now this is not necessarily an exclusive list of things that you can do, but these are all good places to start. Okay, questions so far? Alright, so we're just going to do a few problems. Here is our second example. We've got cotangent equals cosecant theta over secant theta. And I'll go ahead and tell you that unless you have a Pythagorean identity, like 1 plus cotangent squared theta, where you can replace it with cosecant squared theta, if you see secants and cosecants, you usually need to change them, because most of the time we don't want to deal with secants and cosecants. We want to try to get things to sine and cosine. Will make our lives a little bit easier. So the first thing I would probably try on this is I'd try, let's just work just on the right side. I'm going to show you how you could do this either by working on both sides or just by working on one side. Let's just work on this right side here, and let's change cosecant and secant to sine and cosine. So cosecant is 1 over sine theta. And I'm putting parentheses around that because we're about to get a complex fraction, and I start to get confused if I don't put parentheses there. And then secant theta is 1 over cosine of theta. And I'm also going to do this. I'm going to put me a red line right here in between each step, because when I start to get complex fractions, sometimes everything starts running together, and I can't tell what was like the second step and what was the third, or I lose a denominator or I do crazy stuff. So it helps me sometimes to separate these out, especially on the fraction problems. So nothing cancels there. I don't have any trig identities. It would not help me to go back to cosecant and secant, because that would be just what I started with. But dividing fractions is easy as pie. I could flip the second and multiply, right? So that means I'd keep the top. I'd have 1 over sine theta. And I'd flip the bottom. So that'd be cosine theta over 1. And so if I multiply those together, I'm going to get cosine theta over sine theta. And right now, hopefully, if you know your trig identities well, you should be rejoicing, because what is cosine theta over sine theta? It is cotangent of theta. So we can draw our line down here. Cotangent of theta equals cotangent of theta. Okay. A lot of that stuff with fractions, you have to make sure you know about your operations with fractions. So whenever you see that you're dividing fractions, you got to know what to do with it. Now, I did say you could work just on the right-hand side, or you could work on both sides for this problem, because it does not matter what this equals in the end. It does not have to equal cotangent. What matters is both sides have to equal the same thing. So we could have done this. Oops. Didn't mean to erase that much. Let me write this back. 1 over sine of just working on one side, cotangent of theta, that also equals cosine theta over sine theta, right? Instead of changing this back to cotangent, I could do work over here. And so these two sides match, so you're done at this point if you want to do it that way. So you can either work on just one side, or you could work on both sides of the equation. But as long as your last line on both sides is exactly the same, then you're done with the problem. There's going to be some problems where it's really a lot easier to work on both sides. This one is not necessarily much easier. Okay. Questions on that problem? All right. Thank you. All right. Here is our next one. Okay, so we look at example 3. Could we factor anything out? I don't have anything that matches, right? So I cannot factor anything out. Do I have any like Pythagorean identities I could replace? Not really, right? I've not got like sine squared plus cosine squared. I don't have 1 plus tangent squared. I don't have 1 plus cotangent squared. So that stuff is not going to work. So in this case, I do have secant, tangent, and cotangent, all of which I don't really like because I'd rather have sine and cosine. They seem to work out better. So let's, on this one, try changing everything to sine and cosine. So secant squared theta is 1 over cosine squared theta. And tangent is sine theta over cosine theta. And cotangent is cosine theta over sine theta. Now you should see something happening here. Anybody see anything that makes you, what do you see, Matt? Okay, so they're just split. So if I've got a sine on top and a sine on bottom, those will cancel. And if I've got a cosine on top and a cosine on bottom, they'll cancel. But be careful. What do they cancel to? What do they become? 1, not 0. So they're not going all together. But now we've got 1 over cosine squared theta minus 1. So that looks maybe a little better, but it's not anywhere close to being tangent squared theta. Right? So at this point, if you look through those lists of things that we could try, we're working on the most complicated side. We've already trig identities. We've already changed everything to sine and cosine. I can't factor it. I can't multiply it. But I could get some like denominators and add these together. Because right now, this is 1, which is 1 over 1. Right? So if I want common denominators, right over here, my denominator is cosine squared theta. Right? So if I want this to be cosine squared theta, I would have to multiply by cosine squared theta on this fraction. And if I multiply the denominator by cosine squared theta, I must also multiply the numerator by cosine squared theta. We did some of this, but not with trig whenever we were doing those rational equations, right? We were trying to get the denominators to match. Now, the difference is we can't throw the denominators away here. We have to hold on to them. But now we've got 1 over cosine squared theta minus cosine squared theta over cosine squared theta. And since they have common denominators, I can write them like this. 1 minus cosine squared theta over cosine squared theta. Things are starting to run Sometimes I start to get confused with my... Well, that was nice to put those together, but I've got to get this to equal tangent squared theta. Does anybody see what the next step is? Okay. We are I guess 2 steps away, but basically one. When I do this next step, you're going to see what the final step is pretty easily. 1 minus cosine squared theta. This I told you to memorize, right? Because I said it's just as good as an identity. What is 1 minus cosine squared theta? It is sine squared theta. So I can replace that numerator with sine squared theta. Right. So at this point, we should be saying, oh yeah, what does sine squared theta over cosine squared theta equal? Okay. It is tangent squared theta, or you can change tangent squared theta to sine squared theta over cosine squared theta. It doesn't matter as long as what you've got matches at the end. And you're done. That's not the only way to do that problem, but it's one of them. I think the other one's a little harder, so I'm not going to go through doing it that way. All right. Questions? Okay. Here's your next one. This one looks scary, but I actually think it's easier than the last problem. It looks awful, though. I'm actually going to do this problem twice so I can show you both ways to do the problem. If we're looking at this, if we're following the advice that you work on the most complicated side first, which side do you think looks most complicated, left or right? The left is uglier. It's got all this fraction stuff with it. So if we work with that first, here, that's not the only way to do the problem, but if we work with that first, I should have added one more strategy. You might want to add this to your strategies here. There are some times when it can help to do the love connection. Let's go back and add that to our strategies. Do you guys know about the love connection? Okay, so let's add that as a strategy, the love connection. Okay, and the love connection is whenever you have something like 2x plus 6 and it's divided by 4, and then you divide both of them by 4, right? That's where you've seen it before. We haven't used it with trig before. So love connection only works if you have a single term on the bottom, or you have to treat the bottom like a single term, I guess I should say. So let's get back over to where I was at. Okay, so if sin x cosine x is one term because it's multiplied together, so we would divide 7 sin x by sin x cosine x, and then we would also divide 5 cosine x by sin x cosine x. So we would have 7 sin x over sin x cosine x plus 5 cosine x over sin x cosine x. What I like about these problems is, like, there's usually a moment in these problems somewhere, or hopefully there's a moment. Once you get to where you can do these fairly well, There's a moment in these problems where suddenly, like, all the next steps just become clear. And it's like, oh, yeah, if I do this, then this happens, and this happens, and this happens, and I'm done. Right? So I love that moment whenever you realize, oh, I see what's happening here. Now, sometimes you might have to sort of struggle through some steps before it finally sort of becomes clear what's going to happen. But right here, there's something that should be obvious to you that should happen with each term. So right here, is there anything that can cancel? Sine x's. And over here, the cosine x's could cancel. So that leaves me with 7 over cosine x plus 5 over sine x. Now I could keep working on this side, or I could skip over and work to the other side now. So it's just really up to you. This is like 7 times 1 over cosine x. What is 1 over cosine x? Secant. So this is 7 secant x. And this is 5 times 1 over sine x. So this is 5 cosecant x, which matches what you have on the other side. All right. Okay, questions? All right, now I'm going to go back and redo this problem because that's not the only way to do the problem. I won't do this on every problem, but this one is a really good example of why there's more than one way. So you might want to write this down as well, maybe over to the side. We could have worked on the right-hand side instead of the left-hand side. Okay, so if I do that, I would make this 7 over cosine of x, because secant is 1 over cosine x, plus 5 over sine of x. Okay. And then the only thing I could do with those right there is to get common denominators and add them together. So if I've got cosine x for one denominator and sine x for the other denominator, my denominator should be sine x cosine x. So for the first fraction, I would have to multiply by sine x on top and bottom. And for the second fraction, I would have to multiply by cosine x on top and bottom. And so when I do that, they have the same denominator now. I could write them all over the same denominator, sine x cosine x. And I get 7 sine x plus 5 cosine x. That matches this side over here. I kind of don't like that way because your answer is so ugly at the end, but it doesn't matter. As long as both sides of your equation match, you're done. So even if it's not simplified, like on the work you were doing the other night, you were trying to simplify it all the way down to where you got like 1 or 2 or secant x or something really compact, right? On these problems, you don't necessarily have to get a pretty answer at the end. You just have to get both sides to equal each other. So you could do something like this, which actually makes it terrible looking, but as long as it matches the other side, you've proven that that is an identity. So you can do either one here. And really, I don't think there's like one way that's really a lot easier than the other on that. This is not too bad, and the other way wasn't too bad either. So you might even argue this is a little bit quicker. We had fewer steps we wrote down anyway if we did that. So you may do one problem and your neighbor may do the same problem, and they might look completely different, but they could be both right for the problem. All right, let's look at this one, and this will be our last one. We're definitely probably going to want to do work on the left-hand side on this problem because the other side is just 1, so there's very little we could do to that problem, to that side. So we've got sine A over cosecant A plus cosine A over secant A. So what do you guys think? We could get common denominators and add them together, but with that secant and cosecant, I just don't know if that would be the best thing to do yet. So let's make everything sine and cosine. So we're going to have sine of A over cosecant is 1 over sine of A. And then we've got cosine A over 1 over cosine A. And I could get common denominators and add here, but I really would rather not do that while I've got these complex fractions, because that is just kind of ugly to deal with. So how do I get rid of complex fractions? What could I do? Flip the second and multiply. So if I do that for each section here, I'll have sine A times sine A over 1, which I don't really have to write that over 1 if I don't want to. And then here I'll have cosine A times cosine A over 1. So I don't really even have to write that over 1 if I don't want to. What's sine A times sine A? Sine squared A, and hopefully you're starting to have that moment. Maybe you already have, but where you recognize that everything's going to be okay and that this chapter 7 is not going to kill you, although you were thinking it was going to at one point. What is sine squared A plus cosine squared A? 1 equals the other side. Okay? So, lots of different methods that you can use to solve these problems. I have not shown you everything there is to show you yet. Okay? Let me look at the book so I can tell you which ones we're going to do. Alright, our assignment will be on page 434. And let's do 13 through 15. I think we'll skip 16 for right now. It's kind of hard. 17. Let's skip that one for right now. 19 I think we're going to do 20. Let's do those. Okay? So 13 through 15, 17, 19, and 20. What I need to see on every single one of these is that you have tried something, right? Preferably do it right and get all the way down to the answer and feel great about yourself. But try something on all of these. So maybe you don't have a clue what to do, but you can at least change everything to sine and cosine. And then maybe you'll see the next step, and maybe you won't, but hopefully you'll at least get better at these. So you've got about 10 minutes, I think, so go ahead and get started on these right now. We will be working on these. We're not taking any notes tomorrow, but we'll work on more problems like this for the whole class period tomorrow after we have our quiz. We are probably going to have a quiz on these on Thursday. actually being able to do them on Thursday. And the other good thing about this is you know the answer, so you know whether or not you got it right. Well, pretty much, unless you did something crazy that was an illegal move and you just think you got it right. But and I will be here in the morning, but I'll be downstairs if